Hi, this is Audrey Munger, and this is my Lab 3 on circuits. The main goals of Lab 3 are to use a FET simulation to examine the behavior of circuits with resistors and capacitors. Using the results from the simulation, we can measure values of current and potential difference and compare these values to the predicted ones. The major results of experiment 3 are that the measured current in a 2-resistor circuit is 0.02 amperes, and the greater resistance in a resistor, the longer it takes for a capacitor to charge and discharge. Next, I'll go over some fundamental physics concepts that would be very useful to know when looking at this lab. The first is the node rule, which says that the total current entering the node equals the total current exiting the node. The second is the loop rule, which says that the sum of all electric potential differences around a loop is 0. Next is the electrical resistance, which is V equals IR, which can be rearranged to have R equals V over I. In a series, the total resistance equals the sum of all resistances, and in parallel, it's the same relationship but the reciprocal of both. And then finally, the capacitance is equal to the equation there. Next, here are 3 images that show the circuit models that the simulation is showing in this lab, and I took these 3 from the Lab 3 instructions. When creating the circuit simulations, the system we're using is the circuit and the surroundings is everything else. We can also assume that the voltage of the wires and the voltage of the ammeters are negligible. Now looking at the Part 1 simulation, the initial conditions are that the EMF equals 3 volts, R1 equals 47 ohms, and R2 equals 147 ohms. The results of this simulation said that the current equals 0.02 amperes. This value stays consistent because the voltmeter does not conduct a current in the circuit. This is because the circuit is open, so the current can't flow all the way through it. The total delta V is 0, so the loop rule is supported. And when the resistor is added, the current increases because resistance has decreased. And going back to the electrical resistance equation, which is I equals V divided by R, this relationship makes sense. Now looking at Part 2, the first simulation is an RC circuit with a 10 ohm resistor, a 200 microfarad capacitor, and a 9-volt battery. This circuit took 15.4 seconds to charge and 15.2 seconds to discharge. Then we repeated the circuit but changed the resistor to 20 ohms, and this circuit took 25.9 seconds to charge and 27.5 seconds to discharge. This shows that a greater resistance in the circuit causes the charge to take longer to move, meaning the potential difference decreases slower, so the circuit takes a longer time to charge. Now for the plot of the 30 ohm resistor, we recorded the potential difference every second as the capacitor discharges, which this was for 20 seconds. And in the plot of the ln V divided by V naught graph, the slope was equal to -1 over RC and the time constant was 5.98 seconds. Now finally looking at the what if questions, the first one asks, what if you used a real-life ammeter rather than a simulated ammeter? How would it affect the circuits you hooked it up to? So a real ammeter would have a non-zero resistance and real wires on it, and this would cause the current to decrease slightly because there's no way to make actual 0-volt wires. And the second one asks, what if you used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would the capacitor reach full charge? So the wires in the real model have a non-zero resistance, which increases the charging time. The computer model shows the capacitor would fully charge almost instantly, but that's not accurate in a real model, again, because of the wires.